Moving along, shrunken or adjusted R squared is basically a correction that we apply to our observed R squared that is important to do when we have an artificially inflated observed R squared due to too many predictors in our model. So when we have too many predictors in our model, and as k is approaching n, oftentimes we'll have a very large R squared, but it won't be significant. So when that circumstance, if that ever happens to you in the future, that should be a red flag to you to know that there are too many predictors in your model and that they need to be reduced. Another hint of this is when our adjusted R squared and our observed R squared are very far apart from one another. If that's the case, we should know that our observed R squared can't be fully trusted, and we should go with the adjusted R squared, or probably more importantly, delete some of the predictors in our model or reduce them somehow. Okay, so again, the adjusted R squared is a correction that is applied when our observed R squared is artificially inflated due to having too many predictors in our model. We would run a sequential or hierarchical regression rather than a simultaneous one, probably when we have a lot of predictors and we want to group them in some way to understand the incremental variance that is added to the DV along the way. So there's some kind of sequence that we're interested in. So for example, we may have a new therapy technique that we want to test, and we have some demographic variables that we believe will be important to predicting the DV. Let's say the DV is depression or some kind of indicator of a person's functioning. And so we believe that this new therapy will impact that. So we have some covariates that we're interested in. We have a person's age and gender, which we believe will correlate with the DV of interest. So we're going to put them in the first block because they are the ones that, someone's gender and age is something that has been pre-existing way before they ever decided to go to therapy, right? So we're going to put them first in the model because causally they came first. The next thing we may want to do is add a block 2 and put in that block a person's previous counseling experience. So what have they had prior to this new therapy method? And so that is causally comes next. So a person's age and gender is first in the equation, and then we want to see the incremental variance explained by the person's previous counseling and see if that has an effect above and beyond the two covariates. Then let's say in a third block, we want to put in the last block, we want to put in the one that we're most interested in, and that's the new therapy technique. So we're going to put that in the very last step to see its incremental variance explained while accounting for above and beyond the effects of all of those covariates, the age and the gender in the first block, and the previous counseling experience in the second block. And then in the third block is the one that we really care about. And we want to see it, the bump that it gives to R squared. So that would be a perfect case for using hierarchical method rather than a simultaneous method. The simultaneous method is probably best for cases where we have just one predictor of interest and maybe one covariate. So we have, let's say, a covariate of, I don't know, an example comes to mind of the new counseling technique with someone's previous levels of depression. Let's say that's all we cared about. Okay, so we would add those in a simultaneous entry method way, and we would just look at the beta weights to determine if our new therapy explained unique variance and was more important to predicting the DV than was the previous levels of depression the person experienced. So simultaneous entry is simpler. I like it because it's simpler and it's a little bit easier, but the hierarchical gives us more information along the way and gives us those incremental changes in R squared that we are interested in. For the y-intercept in a multi-predictor model, that just simply denotes the expected value of the DV when all predictors are set to 0. And if those have been centered, it is the expected value of the DV when all the predictors are set to their means, and that will equal the mean of the DV in that case. Finally, type 1 error is the probability of concluding that there is an effect because in our sample we found an effect, but in reality there was not an effect in the population of interest. So we made an error in the sense that we concluded that there was an effect when there really was not. Type 2 error is the opposite. We failed to reject the null hypothesis when in the population the null hypothesis is false. So in that case, we have failed to find an effect that really did exist.